Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study the definitions and terminology related to impulse, momentum, and vibrations. Let us begin with what is impulse. Impulse is a quantity of a force times the time interval. The impulse is I equal to F times T. And I is, here it is considered I is the unit for I is Newton per Newton seconds. Now what is the unit for F? F is the force that is in newtons, time T is in seconds. That's why impulse, unit for impulse is the Newton seconds. Now what is momentum? The momentum is the quantity of the motion of your body, of your moving body. It is the measurement of the motion of your moving body. And also here the momentum is mathematically expressed as P is the momentum, mass times velocity. Here the SI unit for momentum is kg meter per second. Okay, the physical significance, as I mentioned here, the quantity of motion, the quantity of your motion of your moving body. What is that quantity? The quantity is that kg meter per second is the quantity. How much? Kg meter per second. Now here, what are the examples of a momentum? The examples of a momentum is that, suppose there are many examples of a momentum. The body is having momentum when the body is under motion. Suppose if the vehicle is traveling, vehicle is nothing but four-wheeler is having certain velocity. If the four-wheeler is having, if the weight of the four-wheeler is some 2 tons, that means 2000 kg, and the velocity of the four-wheeler is 40 km per hour. Okay, is converted into 40 into 1000 by hour, that is 3600. So it is 40 times 5 by 18. That is VF. What is the momentum for that velocity? Momentum of the vehicle, P of the vehicle is 2 tons 2000 times 40 into 5 by 18. If you the calculated value, this is the value with which the momentum, it is the momentum of the vehicle with which the vehicle's momentum is this is the value which will obtain. Now here that means here, if the train is having certain weight, having certain velocity when it is moving, so the quantity of the motion of your moving body is known as the momentum. So there are various examples. Some of the examples are that whenever you toss a ball at someone, as well as it smacks him square in the face, right in the scale, it indicates how difficult it would have been to stop the thing. That's the momentum if you want to stop. So a baseball is swooping to the air, that is also momentum. And a large truck is moving. If the large truck is moving with certain velocity, that means that is also having momentum. Now another one is the momentum is that when a bullet is discharged from a firearm, then it is also having a momentum. So these are the certain examples of a momentum. Okay, and not only these examples, when the ball is hit by the cricket bat, then what will the moment of the ball is moving with certain velocity, with certain mass, that ball is having a momentum. Now coming to here, what is the basically momentum in simple manner mathematically? That momentum P equal to mass is multiplied by velocity. That's just simple. Okay, and here now what is the impulse? Impulse is the rate of change of momentum of your body, and where the time is considered is very small. What is the rate of change of momentum? That is P equal to m into v. That is whatever rate of change of moment. This is the mass times velocity. Rate of change of the velocity, that is dp by dt. Okay, that is m into v2 minus v1 by t. The rate of change of velocity, rate of change of momentum of your body. Now it is m into v2 minus v1 by t. The dp by dt is also known as the force. That force is known as impulsive force. When time tends to 0, limit delta t tends to 0. Limit delta t tends to 0. Okay, then it is known as the momentum. Yeah, that is known as impulse. That is known as impulse. So when delta t tends to 0, now coming here, little bit explanation, F equal to mass times acceleration. What about here? The point is that when time is m into v2 minus v1, mv by t, that is m into dv by dt. Okay. If delta t tends to 0, if it becomes 0, 1 by 0, the force becomes what? Infinity. That force is known as the impulse force. Now these are the bodies are having the momentum, as I explained. When the car is moving and the road is also having momentum. When the aeroplane is moving in the air, is also having momentum. Why it is aeroplane having momentum? The aeroplane is having certain mass and it is moving certain velocity. That's why this aeroplane consists of the momentum P. Now if the vehicle is moving, this vehicle is having certain mass and it is moving certain velocity. This vehicle is having the momentum, that mass into velocity. Next, if we go to the train, here it is having certain mass and also certain velocity. That is mass times velocity is also known as the momentum. Okay. Now coming to the picture of the simple harmonic motion. Okay, here the simple harmonic motion. What is simple harmonic motion here? There are two conditions should be satisfied when the system is under simple harmonic motion or not to justify the simple harmonic motion. What is that those two conditions are? Here the acceleration is always directed towards the mean position and also acceleration is always proportional to the displacement, or the restoring force is always magnitude is directly proportional to the distance and also it is always directed towards the equilibrium position. Suppose if we consider the spring mass system, mass and stiffness, when it is having a displacement x, okay, if you give initial displacement, the spring moves, it is up and down motion from this position to this position, okay, this oscillation is taking place. Now the mass, what is that acceleration? The initial acceleration, that is inertia force is m into x double dot. It is always acts in opposite to the direct active acceleration, active force, that is m into x double dot. Now the acceleration or the force, the force of this mass is always directed towards the mean position. It is the mean position or equilibrium position, and also it is proportional to the displacement x. Alright, the acceleration is proportional to the displacement x. Now what is the equilibrium condition or equation of motion for this spring mass system? The equation of motion for this spring mass system is m into x double dot plus k times x equal to 0. X double dot plus k by m times x equal to 0. That is x double dot, that is here, yes, k by m equal to 0. This is the equation of motion of this spring mass system. Here the simple harmonic motion, the spring mass system represents the linear simple harmonic motion. There are two types of simple harmonic motions. Number one, linear simple harmonic motion, and the next one is angular simple harmonic motion. For linear simple harmonic motion explanation, when the mass, we consider the system of when the mass is attached to a spring. For explaining the angular simple harmonic motion, we'll consider the simple pendulum. When simple pendulum, if we give some angular displacement theta small, it starts oscillating. This oscillatory motion is with respect to equilibrium position, it oscillates. Here also, this simple pendulum satisfies the equations of two conditions, such as the restoring force is always proportional to directly proportional to the displacement, and also it always acts directed towards the mean position. That's why here this simple pendulum is under simple harmonic motion. Okay, now next, what is meant by amplitude of simple harmonic motion? The amplitude of simple harmonic motion is defined that the maximum displacement of the particle from the equilibrium position is known as the amplitude of the simple harmonic motion. How to explain it through pictorial presentation? Let us consider here the mass and it is the k. And if we consider the equilibrium position with respect to time, okay, with respect to time t, the oscillations that takes place. Okay, the time tx. Now this is the maximum displacement from equilibrium position, either upwards or downwards. This is known as amplitude. It is also known as amplitude. But what about another term, the maximum displacement? This is the position x versus a time graph, x versus t. Now what is the time period? Distance that time takes place to complete one oscillation of simple harmonic motion, then it is known as the time period. And what about the frequency? The frequency means the number of oscillations per unit time. That is known as the frequency. Now let us discuss more and more. Coming here, as I mentioned here, simple harmonic motion, keep on explaining. Now the thing main here, the uniqueness, the new novelty in this slide is that here it is directly, that is a of t, that is acceleration equal to minus omega square times x, that is x is function of t. This acceleration. Now as I mentioned here, a equal to minus omega square x, and if we compare with x double dot equal to minus k by m times x. If we compare these two equations, one is related to simple harmonic and another one is equation of motion. Now if we compare, this is also acceleration, it is also acceleration, and x and x, a and a. What is here? The omega square equal to k by m and omega equal to under square root of k by m. So the circular frequency, this omega is known as the circular frequency. The circular frequency comes when the particle is moving circular path and having the simple harmonic motion. Okay. Now next is, what is the difference between the periodic oscillations, simple harmonic oscillation and simple harmonic motion. Here the periodic motion is nothing but examples of periodic motions are uniform circular motion. Here a motion repeats itself after equal intervals of time. Then it is that the motion of those oscillations are under periodic motion. Now here there is no equilibrium position, there is no restoring force, and there is no stable equilibrium position for a periodic motion because it is continuously oscillates. Now next is oscillation motion. What is the oscillation motion? The to and fro motion of a particle with respect to a mean position is known as the oscillatory motion, which the particle moves either side of the equilibrium position. That is known as oscillatory motion. That is what we consider here in the case of spring mass system. The mass moves with respect to equilibrium position, either one side, positive side and negative side, up and down. Then the system is under simple harmonic motion. Now here, the oscillation motion, in order to explain this oscillatory motion, we are considering two things. One is spring mass system, another one is simple pendulum. Now, one more thing is that, what is the equilibrium position? The equilibrium position means it's the position where the system is under stable condition. After giving initial displacement, the system starts oscillating or moving to and fro with respect to equilibrium position. That is the reference line. Now coming to simple harmonic motion, okay, it is a special case of oscillation along with a straight line between two extreme points. Okay, but it should be satisfied the two equilibrium conditions. Now the conditions for SHM, what is the conditions should be satisfied here? F is directly proportional to the displacement and acceleration is directly proportional to displacement. Okay, these are the two conditions. Now coming to types of simple harmonic motions. There are two types of simple harmonic motion. One is simple harmonic motion can be classified. One is linear simple harmonic motion. Another one is angular simple harmonic motion. The linear simple harmonic motion is going to be explained. Linear simple harmonic motion can be explained by using when a mass is attached to a spring. This is what mass is attached to a spring. It gives the linear simple harmonic motion concept. But here, after giving initial displacement along a straight line, what will happen? The body starts moving up and down. Okay, then that motion is known as the linear simple harmonic motion. That example is the spring mass system. The conditions should be satisfied for linear simple harmonic motion is that, again, two conditions. One is the force, which is the elastic or restoring force, is directly proportional to acceleration, is directly proportional, it depends upon the proportional to the displacement of the particle and acted towards the equilibrium position, or either restoring force or acceleration. The acceleration is always directly proportional to its displacement and directed towards the equilibrium position. Now, as I mentioned here, time period and frequency of simple harmonic motion. Yeah, what is the time period here? The mathematically presented as there is 2 pi by omega. Time t equal to 2 pi by omega. What is the time period means? What is the time is taken for completing one oscillation? Then the time is known as the time period. Now the frequency, the number of oscillations per second is known as the frequency. The frequency is the inverse of the time period, or time period is inverse of the frequency. Now here time period frequency equal to F equal to 1 by T, that is omega by 2 pi. Okay, what is omega by 2 pi? We know that from the linear simple harmonic motion, omega equal to under square root of k by m. Now the frequency in terms of the stiffness and mass, the derived expression is F equal to 1 by 2 pi times under square root of k by m. Okay, k is the stiffness and m is the mass. Now one more thing is that this frequency is dependent on stiffness and mass of the system, not on the displacement of the system. That is the meaning here. Now coming to the vibrations. What are the vibrations here? Vibrations is the mechanical oscillations of the object about an equilibrium point. There are various types of vibrations are there. Broadly classified as free vibrations. Number 2 is the forced vibrations. Number 1, it is the free vibrations, and next one is forced vibrations. What is the free vibrations? Coming to free vibrations, in the system is given initial vibrations, initial amplitude, and leave it. Then the system starts oscillating continuously up to some period of time, and after that it comes to rest. Then those vibrations are known as the free vibrations. Whereas in the case of forced vibrations, the spring mass system you consider it, but here we'll give it excitation force F0. Okay, F0 sine omega t. By giving this excitation force, the system will oscillate continuously, okay, without coming to rest. Okay, but because consistently external forces we are giving, then those vibrations are known as forced vibrations. So what are the examples of free vibrations and what are the examples of forced vibrations? If you want to understand it, the forced vibrations comes under the category of the machines when the machines are under operation. When the machines are under operation, or when the engine is under operating condition, under on condition, not in off condition, what will happen? The excitation force acts continuously. Okay, this continuously vibrations takes place. So if you are traveling on your 4-wheeler or your 2-wheeler, so the system, the vehicle is subjected to, or you are subjected to forced vibrations. And what is the free vibrations? Free vibrations are just we give initial vibrations, leave it up, then it starts coming to the rest due to period of time. Then those are known as free vibrations. But the most practical systems, the vibrations are, the forced vibrations are highly important, are highly prominent in nature and also in industries and also both in aerospace and mechanical and civil structures. Okay, these are the forced vibrations and the free vibrations. Now a broad classification of the vibration, there are 3 more types are there. One is longitudinal vibration, and another type is transverse vibrations, and the third one is known as torsional vibrations. What is longitudinal vibration? If you give the displacement, again these longitudinal vibrations, transverse and torsional, can be a force and a free also. If you give initial displacement in the longitudinal direction, the spring mass system in the direction of, in this direction along the axis, and give it up, then longitudinal it starts oscillating. Okay, those are, if you give initial and give it up, those are free longitudinal vibrations. If you continuous excitation force in the direction of the axis, that is the parallel here along the line, then those are known as in the longitudinal direction. Under continuous excitation force, those vibrations are known as longitudinal forced vibrations. Now coming to transverse, in this direction if you give up and leave it up, okay, then it starts oscillating in that direction, then those are known as a transverse. If you give initial with some inclination to the main longitudinal axis and give it up, then those are known as a free transverse vibrations. You are giving excitation force in this inclination to the longitudinal axis, then those are known as a forced transverse vibrations. Now coming to torsional vibrations. In the case of torsional vibrations, we will give the disc. If you consider the disc in a vertical direction, you give oscillatory motion, circular motion, like that. You give up in with some angle, with some angular displacement, give it up. This starts as torsion, torsional free vibrations. If you are giving continuous excitation torque, then you use forced torsional vibrations. So these are the three categories. There is one more category also, damped vibrations. These are the damped vibrations. What are the damped vibrations are? Damped vibration means resistance to the oscillations of amplitude of oscillations of vibrations. Those are known as the damped vibrations. Again, if you want to explain further types of damped vibrations, what are the damped vibrations are? There are three types of damped vibrations. There are three types of damped vibrations. The damped vibrations are number 1, underdamped, number 2, overdamped, and third one is critical damped. Okay, these are the types of vibrations you can study more in detail in the overall view of the session of engineering mechanics in the next class. Okay, these are the references were used here: R.S. Courmy, Irving Shames, R.S. Hibler, R.C. Hibler, and also B. Johnston. These are all coming under the course of the engineering mechanics or references. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.